Welcome back, everyone. Today, we are tackling a topic of global importance and extraordinary complexity: climate change. To understand it, we need to piece together physics, geology, biology, human history, and our planet's future. So, let's begin at the atomic level and build upward to the global challenge we face. First, let's consider Earth's energy balance. Sunlight bathes our planet in energy, some of which escapes back to space as infrared radiation. However, certain gases in our atmosphere, namely carbon dioxide, methane, nitrous oxide, and water vapor, have unique molecular structures. Their vibrational modes match the wavelengths of infrared radiation, meaning they absorb and re emit this energy, heating the air and amplifying warmth near Earth's surface. This is the natural greenhouse effect and is essential for habitability. But this process also sets the stage for global change. If we increase the concentration of these gases, we strengthen the greenhouse effect, warming the planet beyond the natural range. You might wonder, hasn't Earth's climate always changed? Indeed, it has. Over billions of years, our climate has been shaped by natural forces, from a steadily brightening sun to the shifting of continents and the rise and fall of mountain ranges. These forcings exerted their influence slowly, providing time for feedbacks and life itself to moderate change. For example, evolving life drew carbon dioxide from the atmosphere, balancing the sun's brightening and stabilizing global temperatures. But Earth's stability wasn't just luck, it resulted from countless feedbacks. This is the foundation of the Gaia hypothesis, which suggests that living organisms and Earth systems co-evolve, regulating climate and making the planet habitable. Let's follow the thread from natural forcings to more specific drivers. When tectonic plates move or collide, they can trap land at the poles or build mountains whose weathering draws down atmospheric carbon dioxide, sometimes cooling the climate. Now, volcanic eruptions can trigger temporary cooling by ejecting reflective particles into the atmosphere or contribute to warming if massive amounts of carbon dioxide are released over geologic time. To this, we add the rhythms of Earth's orbit and tilt, the Milankovitch cycles, which subtly redistribute solar energy over tens of thousands of years, pacing ice ages and interglaciations. All these factors show that Earth's climate responds to both grand, slow changes and fast, catastrophic events, such as the asteroid impact that contributed to the extinction of the dinosaurs. Each of these forcings would have limited effect without the feedbacks that amplify or dampen climate swings. Melting ice reduces albedo, causing more heat to be absorbed and accelerating thaw. Just one example of a positive feedback. Thawing permafrost releases more greenhouse gases, warming oceans, dissolve less carbon dioxide, raising its concentration in the air. Vegetation and clouds play their roles too, sometimes amplifying, sometimes buffering changes. Feedbacks are what turn gradual or minor changes into the profound shifts we see in Earth's history and in today's rapid warming. That understanding of natural change brings us to the modern era. For the first time, it is not just geologic processes, but human activity that is the dominant driver. Since the Industrial Revolution, we have been burning fossil fuels at an accelerating pace, releasing carbon locked up for millions of years into the atmosphere in just a few decades. This unprecedented input of carbon dioxide, methane, and other greenhouse gases has thickened the insulating blanket around our planet, increasing average global temperatures by about 1 degree Celsius since 1880, with the fastest warming in the last 50 years. Massive land use changes, deforestation, agriculture, urban growth add to the problem, changing both carbon dioxide uptake and local climates. How do we know change is happening? Let's connect the science to the surface. Ice cores and tree rings reveal ancient atmospheric composition and show today's greenhouse gas levels are unmatched in hundreds of thousands of years. Direct measurements, satellites, thermometers, tide gauges show rising temperatures, shifting precipitation, increased frequency and severity of storms and floods, and rising seas. Organizations like the IPCC distill thousands of studies, reaching global consensus. Human activity, especially fossil fuel use, is the main engine of climate of current climate change. What does this mean for our world? The effects are already visible and growing. Sea levels are rising, encroaching on coastal cities and increasing flood risk for hundreds of millions. Changing rainfall and increased evaporation threaten water security, agriculture, and ecosystems. Storms, floods, and wildfires are becoming more intense and frequent. Melting snow and glaciers imperil water supplies for billions. Insects, pests, and diseases are expanding their ranges, changing forests and human health patterns. All these challenges are woven together, each making the others worse. A true web of interlinked consequences. So, how do we respond to this interconnected challenge? Just as climate change is the product of many actions, small and large, solutions require both individual and collective change. From choosing cleaner energy and responsible consumption to advocating for policy and supporting innovation, every action plays its part. Even small steps help. As Margaret Mead famously said, never doubt that a small group of thoughtful, committed citizens can change the world. Throughout today's lecture, we've traced a path from the atomic scale vibrations that warm our air through deep time feedback, geological drivers, and today's anthropogenic impacts, all revealing a climate system that is fundamentally interconnected. With every choice, we are now threads in the tapestry of Earth's climate history. Thank you for your engagement and attention. Make sure you complete your quizzes, you read your text, come for office hours, ask me any questions if you have, attend your labs, and I'll see you in the next lecture.